Welcome back. This is Chapter 7, Video 1, in which we'll be talking about PD, the derivation system for our language P. Now you'll remember that we had SD for our language S, and it had 11 rules. 2 rules for each of the 5 connectives, an introduction and elimination rule, and then we had the reiteration rule. That gave us 11 basic rules. Then, with SDE, the extended system for S, we had a bunch more rules, including substitution or equivalence rule. Now, for PD, we have 2 new logical operators. We have the universal quantifier and, of course, the existential quantifier. And all we really need is an introduction and elimination rule for each of those. So that's going to be 2 times 2 equals 4 new rules. So in that sense, it's very simple. We just need to add 4 new rules. But 2 of these rules are rather complicated. We'll take a bit of explaining. In addition, we'll eventually look at PDE, which is an extension of PD that really just adds 1 equivalence rule. So by the end of Chapter 7, we'll actually have 4 derivation systems. Remember that SDE includes all of the SD rules. Similarly, PD is going to include all of the SD rules. And depending on what your instructor wants, PD might also include the SDE rules. When presenting PD, I will sometimes restrict myself to just the SD rules, and other times we'll use the SDE rules. I will try to make that clear in the discussion. Finally, once we get to see the additional PDE rule, that will of course include PD, which always includes SDE, and again, depending on what your instructor wants, may or may not include SDE. If we include all of the previous systems in PDE, it makes PDE the most versatile of the systems. PDE won't be any more powerful than PD because it's a conservative extension. But PD is of course more powerful than SD because it can deal with the quantifiers where SD cannot. Before we get started, a quick point about some notation and the concept of a substitution instance. Suppose we have some formula P that looks like this. Then the notation P with A for X just indicates the exact same formula, but anywhere X appears in the original, we replace it with the constant A. For instance, given our example P on the left there, if we replace all instances of X with the constant A, we get the following. Now, of course, it doesn't have to be A for X. We could do P, B for X. And in that case, it would look like this. And we could do P, C for X, and so on. Of course, if we had a formula involving a Y variable, then we could do something like P, E for Y, and we'd come up with this. This has nothing to do with valid inference or a derivation rule or anything else like that. It's just a way of indicating that we're taking an existing formula and substituting a constant in for the variables. So there's nothing particularly interesting going on here. It is a purely syntactic notion. Next, we have the notion of a substitution instance. Suppose we took that first example above and put an existential X quantifier on it. So the formula itself would look like this. If we remove the existential quantifier and say put in the constant A everywhere that X appears, we now have a substitution instance of that original existentially quantified formula. Same thing applies to a universally quantified formula, universal X on P would look like this. If we then took off the universal quantifier and substituted in, let's say, C for x, we would get this. Which, of course, is a substitution instance of the original universally quantified claim. And of course, you could do different substitution instances. From the universal, if we took the universal off, we could produce P D for x instead of C for x, and we would get, again, right now, we're not really worrying about a valid inference or a correct application of a derivation rule. We're just defining a syntactic concept of substitution instance. But we'll appeal to this notion of substitution instance in explaining the rules. Consider the following argument. All philosophers are somewhat strange. Gregory is a philosopher, therefore Gregory is somewhat strange. This is a pretty obvious inference for most people, and it's the same pattern of the very first argument we encountered. If you recall, all humans are mortal, Socrates is a human, therefore Socrates is mortal. This is the exact same form, just mixing up a little bit here. Now, how could we reason this out in a way which is painfully logically clear to make sure that we can demonstrate the validity of the inference? Well, consider this. Suppose we number the premises and add an intermediate step. Given that premise 1 says all philosophers are somewhat strange, then we know in particular that if Gregory is a philosopher, then Gregory must be somewhat strange. What we've done here is, from the universal claim in premise 1, we've inferred a particular instance of that, from all philosophers somewhat strange to applying that to me, Gregory. So if Gregory is a philosopher, then Gregory is somewhat strange. Now it should be painfully clear that the conclusion in fact follows. If you take the conditional in premise 3, note that the claim in premise 2 matches its antecedent. And by our most familiar pattern of inference, 2 and 3 combine to give us the consequent of 3, Gregory is somewhat strange. But what's of interest to us here is the transition we make from premise 1 to premise 3. We go from a universal claim to a particular instance of that claim. So what we would like is a rule that allows us to go from claims like all philosophers are somewhat strange to if Gregory is a philosopher, then Gregory is strange. In fact, we will have such a rule. It's called universal elimination. What this rule tells us is, if at any point in a derivation you have a universally quantified formula, then you may do the following. You may derive a substitution instance of that formula. That is, you may remove the universal x quantifier, or it might be a y quantifier or a z quantifier. In any case, you remove the quantifier, and everywhere that the corresponding variable appears in the original formula, you replace it with some constant, perhaps an a, b, or a c. It doesn't matter. Now let's see how using this rule can allow us to do a derivation corresponding to our previous argument. If we set up a derivation to symbolize the previous argument, it will look like this. First premise is a universally quantified claim. All philosophers are somewhat strange as the first primary assumption. Gregory is a philosopher as the second primary assumption. And the desired goal will be Gregory is somewhat strange. Now, the way this derivation sits right now is there's really nothing we can do because line 2 is a simple sentential claim, predicate with a constant, and line 1 is a universally quantified claim. And we can't do anything with the internal contents of line 1, the px arrow sx, until we remove that universal. That's what universal elimination is for. So what it allows us to do is to remove that universal and write out the internal formula replacing the x's with any constant we want. We could in fact replace them with a's here. There would be nothing wrong with that, and it would be coming from 1 by universal elimination. But this doesn't really help us very much because line 2 doesn't actually match the antecedent of line 3, so we can't go any further with line 3. Of course, the strategic point is that instead of PA arrow SA, we should take the substitution instance using the constant G, which in our English interpretation stands for Gregory. That's still one universal elimination. We can do any substitution instance of line 1 with our rule. That constant A can be anything A through U with or without subscripts. But of course we want it to be a lowercase g here, because now, I hope you notice, line 2 matches the antecedent of line 3. So we can use good old arrow elimination to get SG, the consequent of line 3, from 2, 3, arrow elimination. Now, you're probably used to applying arrow elimination and the SD and SDE rules to statement letters, like this. But recall from all our work in translation that any predicate letter with constants counts as a complete sentence, and any truth-functional constructions of predicate letters with constants counts as a sentence. So all of the original SD and SDE rules apply there. Let's take a few minutes to see how we might make mistakes with this rule. The first thing to keep in mind, as I've said, is that the constant A, that's a metavariable A, can be any constant you choose, A through U, with or without subscripts. But the choice of constant is going to depend on your goal, and it's a strategic issue. Finally, you must replace every variable x in the scope of the original quantifier with the constant A. So, going back to the derivation, suppose we wanted to extend this a little bit further with no particular goal in mind, just to play around. One might try to do another universal elimination from line 1 in the following fashion. Remove the universal x quantifier, replace the first x, let's say, with a g again, but then replace the second x with something else, like a c. This is a mistake. Why? Because these do not match. They have to be the same constant throughout, since we have the same variable that we're replacing. Another way to put this is that line 5 just is not a substitution instance of line 1, so we haven't correctly applied the rule. Similarly, we might make this mistake. Again, let's say we put in g for the first x and then leave the second x in there. Well, this also is a mistake. It is not an application of universal elimination because we did not replace every instance of the variable x. Here's another mistake. Students often want to stick in a different variable or even just tear the quantifier off and leave the same variable in there. Some systems actually allow you to do this, but our system is not one of those. Whenever we are removing a quantifier, we're going to be replacing variables with constants, and since neither of these does that, we wind up still with variables in there. These are both mistakes. Let's take a look at two more potential types of mistakes, since seeing what is mistaken is really helpful to seeing how to use the rule correctly. Suppose we had a derivational situation like this. I don't have any particular goal in mind, but I want to illustrate a sort of mistake. Seeing the universal quantifier in line 1, you might think you could apply universal elimination. But as we're about to see, this is going to be a mistake. You might leave the antecedent alone, take the universal y out of the consequent, and put in some constant for that y, and try to claim that that comes from 1 by universal elimination. As I said, this is a mistake, but why? If we look at the rule, what the rule is telling us is that the universal quantifier has to be the main operator of the line that we're going to use universal elimination on. Over here, the main operator is not the universal, but it's the conditional. So since that universal y is part of the consequent and not the main operator for the line, you cannot apply universal elimination there. Here's a similar potential mistake. Suppose we had this derivational situation. Notice here that even though the universal quantifier is in the antecedent, because there are no parentheses around BZ arrow MD, the main operator is still the arrow. So again, if you try to do a universal elimination by taking the universal Z off of there, putting a constant in, this again would be a mistake, since the universal has scope only over the antecedent and not over the whole line, which is what's required by the rule. Finally, let's look at a similar looking situation, which actually is a correct application. First, note here the presence of these parentheses, which extends the scope of the universal over the whole conditional, which means that this universal is the main connective of line 1 as required, which means the universal is the main operator of line 1 as required by the rule. So we can apply universal elimination to this line 1. We remove the universal quantifier, replace that z with a b, and since the consequent doesn't contain any z variables, we don't do anything to it, it stays the same. The fact that line 1 has the constant d in it doesn't require us to use d to replace the z. We can replace the z with any constant we choose. Of course, that includes replacing it with d as well, so this would also be a correct application of one universal elimination. Before we go on to introduce another rule, let's do a couple of quick derivations, see how this rule works. So here we have two rather simple universal quantifications as our primary assumptions, and our goal is a three-part conjunction. If you want an interpretation in mind, you could imagine that all x hx says everyone is happy, and all z ez says everyone is exhausted. And our goal then would be hs for Socrates is happy, hp for Plato is happy, and ea for Aristotle is exhausted. So Socrates and Plato are happy, and Aristotle is exhausted. This is very simple to derive using universal elimination and conjunction or wedge introduction. So let's do it. We need hs and hp, so we can get hs from 1 by universal elimination. We can get HP also from 1 by universal elimination. The fact that we used universal elimination on line 1 to get line 3 doesn't mean we cannot do it again. And then we use universal elimination on line 2 to get Aristotle is exhausted. 3 very simple uses of universal elimination. Now we just need to create the conjunction that we want. We put HS and HP together from 3, 4, wedge introduction, and then put that together with line 5. We get HS and HP and EA, and that is just 5, 6, conjunction introduction, and we're done. There are not a lot of interesting things we can do quantificationally with just the one rule, but let's look at one more quick example. This also is not a terribly complex derivation, but it's worth taking a look at how we can apply some goal analysis here. Our goal here is AB, so we can write that down in at the bottom there. Now, looking around at the primaries, the only place we see the predicate A is here, which with a Z attached, but that's okay because we know that with universal elimination, we can probably replace that Z with a B, getting what we want. You might also notice that lines 1 and 2 internally are conditionals, and that the consequent of the internal conditional of line 1 uses the same predicate letter as the antecedent of the internal conditional of line 2. So that may suggest the familiar use of, say, hypothetical syllogism to link those and drop out the middle. But of course SY doesn't match SZ, and we don't have those on a line by themselves. Both lines 1 and 2 have universal quantifiers attached. But of course, that's where universal elimination comes in. We can rip the quantifier off of line 1, and since B is the ultimate constant we want, that's probably a good choice, and we get PB arrow SB. Now we can rip the quantifier off of line 2 and use B again to replace the Z's. We get SB, then AB. Each of those is a universal elimination. The first one from line 1, the second one from line 2. Now we have a situation where the consequent of one conditional matches the antecedent of another conditional. So if we're allowing ourselves the SDE rules, we can do a quick hypothetical syllogism, which gives us PB arrow AB, and then you'll note that line 3 matches the antecedent of line 6, so with good old arrow elimination, we can get AB from 3, 6, arrow elimination. And we're done. Nice and simple. Now, obviously, there are at least 2 other ways to do this derivation. You could have applied arrow elimination to lines 3 and 4 to get SB, and then use that line with the SB in it, and line 5, arrow elimination to get the AB. One point worth noting here is that even though we have different variables in lines 1 and 2, we use the same constant to create the substitution instance for universal elimination in lines 4 and 5 in order to be able to do the hypothetical syllogism or the 2 arrow elimination steps. And how do we know what constant that is? Well, we see that we have that constant in line 3 and that it's part of our goal. So clearly we want to choose B in doing the universal eliminations so that we can then take the next 2 steps to get to the conclusion. This is a simple bit of strategic choice of constants. As derivations become more complicated, and as we see the more complicated rules to follow, choice of constant is going to become more complicated as well, and we'll talk about it more at that point. Now I think it's time to introduce a second rule. The second of the 4 basic quantificational derivation rules is existential introduction. It's about as simple as the previous rule. It is one of the 2 easier rules. Let's take a look at the rule form and see what the basics are. We'll look at an example in just a minute. So for existential introduction, what we're being told is if at some line of a derivation I, you have some formula that includes a constant, call it A, then you can transition from that formula to an existential claim where we replace one or more of that constant with x and wind up with an existential claim. This is more easily illustrated. So take the following simple argument. Suppose we have the single premise, Fred is a lazy accountant. Well, then we know that someone is a lazy accountant. That is, we should be able to go from an instance of a claim with a name or constant in it to an instance of the same form where we remove that name and use the existential quantifier. That's exactly what's happening here in the transition from Fred is a lazy accountant to someone is a lazy accountant. So this very same argument symbolically would look like the following. We'd have one primary assumption for Fred is a lazy accountant, Fred is lazy and Fred is an accountant, and then we can take that whole formula with an existential x quantifier and parentheses to extend across the conjunction, change both of those f's to x. And that comes from 1 by existential introduction. You can see how, given a claim that talks about Fred in particular, we existentially generalize to the existential claim where the name Fred drops out. Another way to describe what's happening here is that given some formula with at least one constant in it, sometimes there will be multiple constants, you can replace that constant and you can replace one or more. We'll see an illustration in a minute of what can happen if we don't replace all of them. That is, you can replace one or more instances of the constant with an existential quantifier and matching variable. So let's see a slightly different use of this in action. Suppose we had the single primary assumption that Fred loves himself. So notice that the constant f has 2 instances in that primary assumption. One thing we could do here with existential introduction is to replace both instances of the f constant with a variable, choosing z this time just for variety. That is a perfectly fine application of one existential introduction. But unlike universal elimination, where we have to replace all of the variables with a constant, here we can choose whether or not to replace all of the constants with the variable. So take line 1 again. It says LFF, Fred loves himself. But if Fred loves himself, then there is some x such that that x loves Fred. That is also a correct application of existential introduction to line 1. Moreover, we could choose to replace the other f from line 1. So again, starting with line 1, we'll say, for example, some y. It doesn't actually have to be a different variable here, but I'm just choosing one for the sake of variety. If Fred loves himself, then there is some y such that Fred loves that y. Again, this is also a correct application of existential introduction to line 1. If you think it through, it should make sense. If Fred loves himself, then as it says in line 2, there is someone who loves him or herself. Or, focusing on the transition from 1 to 3, if Fred loves himself, then there is someone that loves Fred. Similarly, from line 1, if Fred loves himself, then there is someone Fred loves. So this just accentuates the point that you have choice about whether to replace just 1, 2, 3, 4, or all of them when you apply existential introduction. Notice, and I have no particular goal in mind for this derivation, I just want to show you what we can do, that lines 3 and 4 each still contain a constant. So we could, for example, add another line coming from line 3 by existential introduction, where we replace the f remaining in 3 with an existential quantifier. Now, since 3 already contains existential x, we cannot reuse the x variable, because then we'd have x's overlapping in scope. But we could do the following. Now replacing the f that remained in line 3 with the z. You see we've got some quantifiers with overlapping scope there, so if we're going to do it correctly, they have to be 2 different variables for those quantifiers. Similarly, since 4 still contains a constant, we could existentially quantify into that constant f and replace that f with the variable v. Again, just chosen for variety, no need. And so that is for existential introduction. So it's a pretty simple rule. You can go from a particular instance to existentially generalized forms of that instance. The only minor complication, of course, is that you can choose whether or not to replace all of the constants if there are multiple instances of the same constant. One thing to keep in mind in order to avoid a potential mistake is that if you're replacing multiple instances of a constant, they must be the same constant. So, for example, the following maneuver would be a mistake. Suppose we had something like this. Fred loves Susie as a primary assumption. It would be perfectly legitimate to go from 1 to some x, lxs, someone loves Susie, by existential introduction. Or we could also go to, I'll use a different variable here, some y, lfy, Fred loves someone. But unlike the previous example, where we had Fred loving himself, we have 2 different constants here. So it would be incorrect to try to replace both of those constants in the same existential introduction. That is, this is a mistake. Someone loves himself should not follow from line 1 that Fred loves Susie. So the idea that that would be existential introduction is a mistake. A mistake I'm sure you will not make once you have some practice with these rules. Now, like before, given that lines 2 and 3 here still contain a constant, we could add an additional quantifier. So from line 2 that says someone loves Susie, we can get someone loves someone. That would be 2 existential introduction. And we can get a similar formula. They're not exactly the same, syntactically speaking, from line 3. 3 says that Fred loves someone, so we can existentially introduce into the position where the f constant appears, and we get someone loves someone from 3 existential introduction. Note that in this example, unlike Fred loving himself, we cannot get some x lxx, because the f and the s in the primary assumption are 2 different constants. When we apply existential introduction, we're going to wind up with 2 different variables. Let's take a look at a fairly simple derivation that combines each of the 2 rules we've been looking at. So here we have 4 primary assumptions, and our goal is to get some y, my, and ky. Now, if we put that goal down at the bottom of our derivation, then it's likely that our very last step will be justified by existential introduction in order to get that as the main operator of our goal. That means that the previous formula is going to have to look like this, where some constant is the same constant is filling in the blank on the M predicate and the K predicate, so that we could then apply existential introduction to get the final line. The question is, what constant should that be? Well, it's not entirely certain at this point, but the fact that the constant d appears in the primaries suggests that that might be the way to go. So let's work on that assumption for now. That gives us the sub-goal of MD and KD. Now, if we look at the primaries and see what materials we have to work with, M and K each appear as the consequent in some universally quantified conditional. So I know that I could use universal elimination to get FD arrow MD and BD arrow KD. Let's do that. Give it a try. So from line 2, I can remove the universal x and replace the instances of x with d. That gives me FD arrow MD. So that is 2 universal elimination. I can do something similar to line 3 and get BD arrow KD. And now I see if I can just get FD, which in fact I have in line 1, that'll help me get the MD. And if I could just get BD, that would help me get the KD. Now, line 4 tells me that every x is B, so I can use another universal elimination here on line 4 to give me BD. And then 2 quick arrow eliminations, 6 and 7, together get me KD by arrow elimination. And then 1 and 5 get me MD. And those two together will give me this, which is now line 10. It's 8 and 9 conjunction introduction. And then having MD and KD, I can apply existential introduction to get some y, my, and ky, which is the goal. And we're done. In Chapter 7, Video 2, we'll cover the other 2 of the 4 main quantifier rules: universal introduction and existential elimination.